So this is page 229, deals with concavity. Just a quick rundown of this. I'm not going to bother to write this down. As this comes out of my mouth, it should make sense to you. The critical points of the first derivative tell you points that you're suspicious may be maxima or minima. First derivative. In order to confirm whether those critical points of the first derivative are truly maximum or minimum points, you have to do a first derivative analysis in the form of a first derivative chart, normally. There's other exceptions, of course. If you have a closed function, you can just make a table of values and see what the largest y is and what the smallest y is. Moving on to concavity, the second derivative has critical points, and by the way, critical points are any values of x that make the expression 0 or undefined. The second derivative's critical points are points that you are suspicious may be inflection points. And it's a little bit different in a lot of ways than the first derivative critical points. One of the ways it's different is the critical points for the first derivative may be a maximum or a minimum or neither. When it comes to inflection points, there's only one type of inflection point. There's not like a maximum or a minimum. There's just an inflection point. So the critical values of x for the second derivative tell you where potentially inflection points could be. But in order to confirm whether or not they are inflection points, you need to do a second derivative analysis in the form of a second derivative chart. And the other thing that goes along with this in comparison, again, is that when a first derivative is positive, the function is increasing. And when the first derivative is negative, the function is decreasing. Whereas when the second derivative is positive, the shape of the function is concave up. And when the second derivative is negative, the shape is concave down. So where a function goes from increasing to decreasing is a max, where it goes from decreasing to increasing is a min, but anytime the concavity changes for the second derivative, you have an inflection point, as long as the function is defined. Does anybody have any questions you would like me to go over here from this section? Go ahead. F. So we have x to the 4 minus 24x squared plus x minus 1. And this isn't a full-blown analysis. We're going to have to find the first derivative to get to the second derivative, but we're not worried about max mins. Okay? So we start off with the function. You said f, right, Miles? Okay. We start off with the function, and we differentiate it. In this case, we get dy dx equals 4x cubed minus 48x plus 1. I'll double check that. That looks okay. Again, if you were going to do a full-blown graphical analysis of this function, you would stop here and find the critical values of x, or come back later and find the critical values of x. So you could do a first derivative table, but we're not asked to do that, and we don't need to do that. We're after the inflection points or intervals of concavity, which means that we have to take the second derivative, which gives us 12x squared minus 48, which in factored form is 12 times x squared minus 4. So I can take the 12 out to make my life a little bit easier in finding the critical points. If you don't take the 12 out, you'll still get the critical points, but you'll just have to do a bit more work. This factors further into d2y dx squared, the second derivative, equals 12 times x plus 2 times x minus 2. We get two critical values of x, plus or minus 2. Not that it's really important because, again, we're not analyzing the graph here in detail, but the fact that I got two critical values of x brings up the possibility of symmetry for this function. And I don't know, if we go back to the original function, I'm mistaken though, it's not symmetric. There's no symmetry because we've got an even degree, and then all of a sudden the degree on x is odd. So that mixture throws symmetry out the window. Maybe it's good that I pointed that out to you. Just because you have symmetric critical points doesn't mean the entire function is symmetrical. Okay, so now what? Now we're going to do a second derivative analysis by going from negative infinity to negative 2, from negative 2 to positive 2, from positive 2 to infinity. Just again, this is my double check all the time, is to say if there are two critical values of x, then when I slice up infinity, I get three pieces. Across the top, I'm going to have 12 and x plus 2, and I'm going to have x minus 2. And for the sake of this analysis, I'm going to treat that as one thing. I don't know how much we've discussed this in the past, but you understand you could probably not even write the 12 because it's positive, but I would prefer that you put it and include it somehow. This will be negative until it passes the 0 of x plus 2, and the 0 of x plus 2 is negative 2. So this is what's going on there. X minus 2 will be negative until it passes the 0 of x minus 2, which is at 2. So the second derivative is positive, then negative, then positive, which means the function is concave up, concave down, concave up. Now you don't just look at that chart in a vacuum. You have to look at everything else that's related to this chart. Namely, is the function defined everywhere? Because to say that we have inflection points at negative 2 and 2 is fine, but the function has to exist there, right? And it does. I mean, I'm not pointing out that there's something weird going on here. I'm just pointing out we have to look at the fact that this is a polynomial function which is defined everywhere. So the fact that it changes concavity at negative 2 and at positive 2 means there are inflection points. So in answer to the question, this function would be concave up on negative infinity, comma, negative 2, in union with or as well as 2 to infinity, and it's concave down on negative 2 comma 2, and we have inflection points at negative 2 comma something and at positive 2 comma something. Just to complete this, I'm going to put positive 2 into the original function and ask you to do the same thing. Oh, yuck. 16, 17, 18, 17. I want to say negative 79. But I've not been having a particularly shining day today with numbers. It is. Wow, finishing on a high note. Negative 79 when I put 2 in. When I put negative 2 in, well, it's going to change by 3. It'll be negative 82, I believe. So there's that evidence of non-symmetry here, because if this was symmetric in some way, then getting negative 79 would give you positive 79 on the other side. Is it negative 82? Did anybody bother to check? Sorry?
Negative 83 is what I got.
Oh, actually, yes, that makes sense. Thank you. It's funny, I said negative 82 and I wrote negative 84. But if we split the difference, it's actually negative 83. Okay. Is that okay, Miles? Yeah. Does anybody have any further questions before we get started today? All right, so we're going to move on. This is a very short lesson, but it's going to bring up an idea here that leads to this conclusion. You have options when you want to find certain features of graphs. You don't always have to find maxima using the first derivative and the first derivative chart. And that's the first thing I want to explain to you getting out of the gate here. There's not a typing mistake on the screen here right now, nor is there one in your notes. We're going to be using the second derivative to find maxima and minima. And it's not always going to be something that works. This is called the second derivative test. So it is not about concavity. It is and it isn't. It includes concavity, but we're using it to determine maxima and minima. And like I said, it's a very quick lesson. There's not much to it, but then we're going to have a variety of different examples that you can try where you may choose to use the second derivative test, or you may choose to use the first derivative and the first derivative chart. Now, don't get me wrong. If you're going to use the second derivative test to do something, you need to know the second derivative, which means you have to find the first derivative to get to the second derivative. But it just turns out that sometimes it's a lot easier to find max mins with the second derivative test rather than using a first derivative table. Okay, so let's run this through. We already know that the first derivative gives you critical values of x. So the critical values of x are values of x that make the first derivative 0 or undefined, and just a big comma parentheses statement. In using the second derivative test to find max mins, you would probably only ever use what we're going to learn today when the function and the derivative are defined everywhere. There's no anything being undefined. If the first derivative is undefined someplace, the second derivative test is not a good idea. Okay? So the critical values of x, the values of x that make the derivative equal to 0, we'll just leave it at that, are considered potential points where max min exist. And normally what you would do is then build a first derivative table and look at where the function is going up and where the function is going down and see where that leads you. So we've called that the first derivative test. The second derivative test is not what we did yesterday and the day before. The second derivative test is not finding where inflection points are. It's finding where max min are. So, before I explain it to you, and I've kind of been leading up to this thing, this second derivative test to find max mins, doesn't always work. Okay? Doesn't always work. Which is not a good thing. It's not a multi-purpose tool. It really isn't. It isn't something that you want to carry around with you to solve all your problems. Why would we use it? Because when we can use it, it makes it very simple. That's the bottom line. When you can use the second derivative test to find max mins, it's quick. And for some functions, it will identify all max mins, specifically polynomial functions. And polynomial functions are defined everywhere, right? They go up and down in different places, depending on the degree. They'll have a certain number of x-intercepts. But they're defined everywhere, and the second derivative test works beautifully for them. So what is the second derivative test? Look at what this says very specifically. If f prime of c, c is a critical value of x. If f prime of c is 0, let's just stop there. If f prime of c is 0, and it's a polynomial function, there must be a max or a min there. There's a lot of logic in what we're talking about today, and in this course in general. We started off with the first derivative saying, if the first derivative is 0, then, actually, I take back what I just said. We started off by saying, weeks ago, if the first derivative is 0, there may be a max or a min there, right? Okay. I just said if it's polynomial, there must be, and I take that back because there's an exception. If f prime of x equals 0, there's likely to be a max or a min there. Let's take a break here and a breath. How could you have a polynomial function whose derivative is 0 at a point and not have a max min there?
Could it be that that's a point of inflection?
It is, and it happens to be a very special point of inflection. It's not a point of inflection that looks like that, because the derivative there would not be 0. Do you see that this is concave down here and concave up here? Okay. The derivative is not 0 there because the slope is still positive. It's a very special type of inflection point that has, at that instant where it inflects, a slope of 0. Okay. Can you answer this question for me? That's not a max min, but the first derivative is 0. What is the concavity at that point? Is the concavity positive or negative? In other words, is it concave up at this point or concave down at this point?
Neither.
It's neither. That's the definition of an inflection point, right? Okay. Would you agree that this is a case, also a case, where the first derivative is 0 at that critical point? Would you agree that it's 0 because the slope is positive? Or sorry, the slope is 0. Okay. What is the concavity at this point?
Down.
It's down. It's a negative concavity. If that were the case, if it's concave down and the slope is 0, that has to be a maximum, doesn't it? And if the slope is 0 at a particular point and it's concave up, that has to be a minimum. That's the second derivative test. Whoops, didn't want to hit that one. That's the second derivative test. If the first derivative is 0 and the second derivative is positive, there has to be a minimum there. Right? The only way the first derivative can be 0 is if the slope is 0. The only way it can be concave up is if it has that general shape. So that point must be a minimum. Conversely, if the first derivative is 0, but it's concave down at that point, then you have to have a maximum. That's the second derivative test. If you can figure out that a function has a first derivative that's 0 at the number 2, and you put 2 into the second derivative and get a positive answer, then it's concave up there and it's a minimum. If you put that critical value of x into the second derivative and get a negative result, then you know it's concave down. And the slope is 0, so that's a maximum. If you put the critical value that you find of, say, 2 into the second derivative and you don't get positive or negative, you get 0 or undefined, then it's not a max or a min. It's something else. So let's put this into practice. Use the second derivative test to find all extrema. So the reason why you would use this, and I know I've said it already a couple of times, but I'll repeat myself. The reason why we're going to use the second derivative test is it's a polynomial function. And finding the first derivative is needed for two reasons. Because we need to identify the critical values of x for the first derivative, but we also need to determine the second derivative, so you have to go through the first derivative first. The first derivative is the door that leads to the second derivative. So the first derivative is 6 times x squared minus 1. I hope Everybody is okay with that factorization kind of in one shot? Which tells me that my first derivative critical values of x are -1 and 1. My second derivative, well, just going from here, my second derivative, d2y dx squared, is 12x. So my second derivative at those critical values of x, that just means I'm going to put -1 into my second derivative, and I'm going to get -12. I'm going to put +1 into my second derivative, I'm going to get +12. You know, there's a lot going on here, and I feel as though maybe I might be overcomplicating things, but this stuff is telling you that the slope of the tangent is 0, right? That side of the table is telling you that at those points the slope of the tangent is 0. This side is telling you that at -1 it's concave down, and at +1 it's concave up. And this bit of business over here, everybody, I wouldn't recommend memorizing that. That's thinking about things. What does it mean to say concave down but having a slope of 0? It must be that this is where the slope is 0. So what that means is we have a maximum at -1, comma something, and a minimum at 1, comma something. And then it's a matter of putting 1 into the function and -1 into the function and calculating the y coordinate, which I would like you to do. Mainly so that you get the practice and also that you can check my mistake, check my math. No, it was right. I'm pretty sure it's 18. No? Negative, oh, geez. Is the 18 right? No. -2 plus 19. Oh, man. 17? Okay. And then we're putting 1 in. I'm pretty sure I had that right, 9. Yeah. Okay. And this is what I mean when I started off by saying you have options. Some of you might not like this. I'll admit it does require a little bit more thought, because normally you just do the table and you've done so many tables, you get on autopilot and you just do it. But I want to make a point. Yes, you have options, but sometimes on an exam I'm going to ask you about the features of the graph in terms of the first and second derivatives. So I should be able to draw any graph with cusps and maxes and weird inflection points, and I should be able to label a whole bunch of points, 1, 2, 3, 4, 5, 6, 7, 8, 9, and say, what can you tell me about the first derivative and the second derivative at each of those points? All right, let's try one more. I mean, this is a fairly simple function in terms of analyzing it. There's not much to it. I'm going to do the prime notation this time. 8x cubed minus 3x squared. Speaking of autopilot, I got to always remind myself I was forgetting this a lot today in my classes, to slow down and think rather than just automatically being on autopilot. So double checking things. We got 4 times 2 is 8, x cubed, but that's okay. Let's just find the second derivative. And I believe that's okay. The critical values, well, man, you know me, I don't like writing equals, equals, equals. I think it's a really bad move in math, but we're just kind of in learning, teaching mode right now. I can take out an x squared and have left 8x minus 3, which means when I start talking about my critical values of x for the first derivative, they are 0 and 3/8. When I start talking now about the second derivative at those critical values of x, I hope you understand my xc in my notation in this table is not f double prime of the critical values of the second derivative. It's of the first derivative. So I put 0 into the second derivative and I get 0. I put 3/8 into the second derivative. My brain is just not cooperating. I'm going to have to go to my calculator for that. I know 3/8 is 0.375. Do you get, well, 1 1/8? Do you get 9/8? Okay. But the important thing here is you get positive 9/8. So what is happening at x equals 3/8 is we have a minimum. And I don't know if you noticed that little stutter in my words there, because I was thinking. I was going, okay, wait, a positive second derivative means it's concave up. So I thought of that in my head, and I pictured something that was concave up so that I could look and see that there's a minimum. Nothing here. Well, there'll be an inflection point, I suspect. But in order for you to determine if there's an inflection point, you've got to do a full-blown second derivative analysis. So we will have a minimum at 3/8, comma, whatever we get when we put 3/8 in for x. And that's just a trivial matter of figuring out what that is. 2 times 0.375 to the 4 minus 0.375 cubed. Couldn't even begin to tell you what that is. Negative 27 over 2048. Okay, well, we have time here. That's the lesson. As I said, you're going to be getting practice with this and some other things today. But let's just double check something here. Let's graph this on our graphing calculator. We should be, and then setting up our window settings so that we would see these key points that are a max and a min. Even though there's not much of a challenge to graphing it on your calculator, I always find it interesting or rewarding to see the result. I'm going to put my window settings from, I'm going to go negative 3 to 3 for x, and probably 0 to 20 is good enough. So let me go to my calculate menu and choose minimum. Put my cursor to the left of that minimum I can see, put it to the right. You get 1 comma 9. And you can continue. Well, we'll do it together. Let's do the same thing on the other side. I don't know in this class if I've often said this or ever said this. You don't have to scroll to the left. If I know that I went from -3 to 3, I know that the number looking at that that -2 will be to the left of it. So I can just enter -2. I don't have to scroll to it and then go enter. And then I can enter a value of x instead of scrolling to a value of x, like 0. And you get 1 comma 17. This next one, if you were to graph it, y is equal to 2x to the 4 minus x cubed. And if you didn't do any work on paper, and you just went zoom 6, it just looks kind of like a parabola of a sort. But there's a max min in there, right? Well, not a max min. There's a min in there at 3/8. And you would probably suspect, looking at that graph, that the minimum is at the origin. But we can set up our table to go from maybe -1 to 1 for x. And, look at the y coordinate of the minimum. It actually goes in a negative position. It's below the x-axis. So I'm going to go from negative, I'm going to look at this and say that this is about 0.01. Just very approximately, because 20 over 2,000 is 0.01. So I'm going to go from -0.02 to 0.02. And I might have to adjust that in a bit, but now if I graph it, like, you would not have seen that. And by the way, I'm now going to graph it in a little more detail by changing my window settings. And you can see, shouldn't have gone that far, 0.75. You can see that it does have a slope of 0 at the origin. The first derivative is 0, but there's that inflection point. That's the very special inflection point where it bottoms out slope-wise. As it's inflecting, it's not going up or down. It's perfectly horizontal. But once again, if you take a look at that, clearly, if you would have just gone zoom 6, you wouldn't even know to look in there to see if there was something interesting going on. I suspect even if you just went from -0.5 to 0.75 without adjusting the y, you still wouldn't see it. You see something coming here and it's probably going to go up. You would really need to expand that vertical view. All right, so there are some questions on page 232 that are about finding max mins. And I want you to notice, I don't have them here, I have them here. I want you to notice that question 1 has, for the most part, all polynomial functions. This j is not a polynomial function. So there's a non-permissible value there, and I'm a little puzzled as to why you would want to use the second derivative test here as opposed to just using the first derivative chart for j. But these ones, you're kind of being guided to use the second derivative test. When you get to 2, it says use any method, and the reason is you would not use the second derivative test for anything except for, even this I kind of balk at a bit, but this one's okay because it's defined everywhere. But these other ones have non-permissible values or they are rational functions. So the second derivative test is not a guarantee. I also have, it's not really like a tough challenge, but this polynomial function on the board, which I'm going to write on the screen so that you can see it, Braden, it's y equals 3x to the 5 minus 10x cubed plus 45x. It's not like a really tough challenge, okay? It's not that tough. I want you, if you have time today and you want to, you do a full-blown first derivative analysis or a second derivative test to find out if there's any max-mins. I also would want you to do a second derivative analysis to find out if there are any inflection points. And the results you're going to get are challenging to put together to tell what the graph looks like. It's a really surprising result. And I don't necessarily, well, I don't want you just graphing it on your calculator because, oh, it's an interesting result. I don't think you'd really see much of anything on your calculator. In fact, when you get the results from your first and second derivative analyses, whatever they involve, and you compare it to your calculator's graph, you might wonder what's going on. Your calculator cannot graph the subtleties that you can graph. Anyway, that's it for today. That's all we're working on. You have about 40 minutes to practice the second derivative test, which, as I said, you do need to know how to do, even though you may not want to go that route. And you can try that one as well. When we come in on Monday, I still haven't really decided. There's one section at the end of this unit that is totally elective, and some years I do it and some I don't. I really want to do it with you as a group, so that may push our exam to it. Well, it'll push it to at least Monday, but maybe Tuesday, of not this coming week, but the week after. And we have lots of time, so don't worry about that. So get to work, please.